Okay, good morning, students. Welcome to the class. And today's topic is variation of the conductivity and molar conductivity with the concentration. You know that yesterday we have seen that the conductivity was calculated as kappa, right? And molar conductivity was calculated as a cap m. Okay, and there was a relationship between them that was cap m is equal to kappa by c. At a particular concentration, the conductivity is called as a molar conductivity. And to convert it into the centimeter cube, we need to multiply it by the 1000. Fine. If you see that if the conductivity is constant, right, and then you can say that molar conductivity will be inversely proportional to the concentration of the solution or the concentration of the electrolyte, right? So what is the meaning of that? It means that if you decrease the concentration, then molar conductivity will increase, and if you increase the concentration, then molar conductivity will decrease. Is it fine, students? So this is the relationship, and you need to keep this in the mind, right? So we'll see that what happens when you decrease the concentration of the electrolyte with the molar conductivity. What happens in the molar conductivity when you decrease the concentration? So here you can see that decrease in the concentration increases the molar conductivity. Okay. So we have seen the formula that was conductance. Conductance was equal to what? Kappa into area of cross section upon L. Yesterday we have discussed this one. Suppose if you keep that area as unity and the length is unity, then you will get the G is equal to kappa. That means what? If the conductivity of a solution will be equal to the conductance when the area is taken as unity and the length is taken as unity. Is it fine? Resistance will not be used. I used that wrong part. You can use the conductance. So conductance of the conductivity of a solution will be equal to the conductance when the area of cross section area of the cell will be unity and length will also be unity. Is it fine, student? So now this was the formula for that, and if you calculate the molar conductivity formula was can be taken as cap m is equal to kappa into A upon L. Fine, student. So if length is taken as unity, then what will be the area? Area can be taken as volume. Volume is what? For the 1 mole of the substance, what will be the volume? So the formula will be taken as cap m is equal to kappa into V. So at a particular volume, volume will also be fixed, and at a particular volume, the conductivity will be considered as a molar conductivity. Is it fine? So this was the relationship. Ultimately, you need to concentrate more on that. This is the most important part which you have to see that. Fine. If what happens when the concentration is decreased? Is it fine? The molar conductivity will increase. And if what happens when this part is the concentration is increased, then molar conductivity decrease. So if you plot a graph between the concentration and this part, then it will come as a slope, negative slope. Is it fine? My question is to you that what happens when the concentration is decreased? Here you will see that the concentration is increasing and increasing. And the concentration increasing, then molar conductivity will be decreased. So here you will see that this is coming. The concentration here, this is the less one. So molar conductivity will be concentration is increased and molar conductivity will be increased from this graph. Now the question is to you that what happens when the concentration is decreasing? That means we are diluting the solution. Is it clear? So if you dilute the solution, dilution means we are just adding the water in the electrolyte. So just adding the water in the electrolyte, then what happens? The concentration will be decreased and it will be reaching to the zero. That means what is reaching to the zero? The concentration will be reaching to the zero. That means the concentration will be zero at here. Is it fine? At this point, then what will be the molar conductivity? That has to be calculated. So here what happens for calculation of the molar conductivity when the concentration reaches to the zero? And when will be the concentration zero? When the more and more amount of the solvent is present in that. That means the infinite dilution, we can say that. So at infinite dilution, what happened? What will be the conductivity? Molar conductivity. Is it fine? And at infinite dilution, the concentration will become zero. So you will see that when will be the concentration zero? When you bring the concentration this side, that means we have to extrapolate the graph. So this is called extrapolation of the graph, and at this point you will get the cap m. Is it fine? So the concentration will be zero. Below zero you cannot take the solution. So this is the limit of this. So this will be the maximum molar conductivity. That means what? At a concentration 0, what will be the molar conductivity? This will become this has become 0, or we can say this is not 0, this is called as a cap naught m, or this can also be considered as a cap infinite m. Understood? Or cap naught m. So what is the meaning of that? Here we need to conclude that whenever you add a solvent in an electrolyte, solvent means water. Is it clear? So suppose if an electrolyte is taken, then you know that the number of ions are present at a particular concentration. You know that. But if you add more and more amount of the water in that, then concentration goes on decreasing, and one stage will reach where the concentration will be reaching to the 0. Then molar conductivity is called as a limiting molar conductivity. That means this is the limit at which the molar conductivity will be maximum. Is it fine? Because of the formula, right? But if you represent it graphically, then how will you find out the limiting molar conductivity? Limiting molar conductivity is that the conductivity at the infinite dilution. The molar conductivity at the infinite dilution. Is it fine? This is called as a limiting molar conductivity. So at infinite dilution means what? Infinite dilution means the concentration will be 0, and concentration will be 0 when you plot this graph. This is called extrapolation, and you will get at this point, this is the limiting molar conductivity. I hope you understood this thing. So what is the correlation between all these things? Conductivity means what? The reciprocal of the resistivity. Okay, this is the first part. What is the molar conductivity? The molar conductivity is at a particular concentration, the conductivity is called as a molar conductivity. And what is limiting molar conductivity? When the solution is diluted infinite times, then concentration reaches to the 0. That means at a particular unit area, 0 ions are present. Is it fine? So if the 0 ions are present, and whatever the conductivity is called as, that is called as the limiting molar conductivity. So there are three things: kappa, cap m, cap naught m. Is it clear, student? Then what will be the relationship between this part? How will you obtain this thing, or how will you, what will be the relationship between the cap m and the cap naught m? So, you know that this is for the strong electrolyte, and what is the relationship? This is the cap m. Cap m is what? Molar conductivity will be equal to limiting molar conductivity minus A and C to the power half. Is it what? C is what? Concentration. A is the constant for the particular temperature. If you change the temperature, the A's value will be vary. So this is the constant for the particular temperature. You can say A can be calculated as for NaCl 1 minus 1. 1 is the valency of Na, and minus 1 is the valency of the Cl. CaCl2 is what? Valency of Ca is plus 2, and chlorine valency is minus 1. Okay, MgSO4 2 minus 2 is there. That means the valence. So we can substitute the value of A, and we can find out what? Molar conductivity or limiting molar conductivity. By using these values, we can find out the molar conductivity and the limiting molar conductivity. I hope you understood this thing. So in the strong electrolyte, you have seen that we can obtain the limiting molar conductivity by just infinite time diluted form. But just come on the weak electrolyte, and we have seen by this drawing the graph, and we found that we can just find out the limiting molar conductivity by extrapolation of the graph. Right, now the next thing is for the weak electrolyte. You know that weak electrolyte means what? The dissociation is less. Dissociation is very low. Is it fine? So whenever you are diluting it, the dissociation will be continued. So due to this, what happened? The limiting molar conductivity of the weak electrolyte is not possible. So then for this purpose, if you want to find out the limiting molar conductivity of the weak electrolyte, then what to do? Is it clear? So that time the new law is introduced by the Kohlrausch, that is called Kohlrausch law of independent migration of ions. What Kohlrausch law did? Actually, he selected a few of the electrolytic salts. Is it fine? And he made the groups. Is it fine? In some groups the cation was same, or in another group the anion was same, and he found out the differences between these groups. Is it fine? And he found that the limiting molar conductivity of all these groups was coming same. Are you getting me? What was the group? In the group number 1, so there is a difference of if cation should be same and anion will be different. And the second group, that anion was same and cation was different. But if you find out the difference in these groups, you will see that the value is coming same. Is it clear, students? So from that, he concluded that that's not the whole salt which is participating in finding out the limiting molar conductivity. This is an independent ion that is an individual ion which is responsible for the calculation of the that limiting molar conductivity. That is why he called it as a independent migration of ions. So this is called as a Kohlrausch law of independent migration of ions. So just see that how he made the groups. He found out that limiting molar conductivity of the KCl and limiting molar conductivity of NaCl. So what thing is common? Chlorine is common. That means anion is common. Is it fine? That's cap naught M. The same second group is there, cap naught M KBr minus cap naught M NaBr. That was the second group, in which what happens? The bromine is same. It's fine. The third one, he made that cap naught M like Ki and cap naught M Nai. So here cation is same. So whatever the value was there, the value was coming same. That means what? 23.4. So everywhere he saw that if you are keeping either cation same or anion same, and if you find out the difference, the value is coming more. That means everything depends upon the one of the species of the ion. Either it may be the positive ion or it may be the negative ion. The same way he made the another group this one, cap naught M NaBr minus cap naught M NaCl. So here the cation is common. Again cap naught M KBr minus cap naught M KCl. The value was coming what? 1.8. That means it is also same. Is it fine? So finally we found out that it is one of the ion which is responsible for this limiting molar conductivity. Is it fine? So for the individual, how will you calculate? How will you calculate the individual salts, electrolytes limiting molar conductivity? So he gave that limiting ionic molar conductivity. So limiting ionic molar conductivity will be denoted as a lambda. So if NaCl is ionized, then it forms the Na plus plus Cl minus. So for Na it will become lambda not Na plus lambda not Cl minus. So independent molar conductivity of the sodium plus and independent molar conductivity of the chlorine. As the same way, if you take the CaCl2, so for the CaCl2, what happened? Ca2 plus charge and 2 chloride ions will be produced. So for this one, it will become lambda not Ca2 plus, that is for the individual Ca2 plus, and this will become 2Cl minus. I have multiplied the whole thing by 2. Why is it so? Because after ionization, what happened? 2 chloride ions are produced. So this will become 2 lambda not and Cl minus. Understood this thing? So this will be the individuality of the limiting molar conductivity, and after finding out, we can substitute these values. We can see that the difference is coming same. So what is the conclusion? Here the conclusion is that limiting molar conductivity depends upon the individual ion. Is it clear? But now in case how will you prove graphically? This is the most important part. So when you draw the graph of the acetic acid, so if you take the acetic acid here, CH3COOH, then how will you find out that limiting molar conductivity? I told you the limiting molar conductivity is not possible theoretically as well as graphically. So if you plot a graph, that time the graph will come like this. Is it clear? So these are the points. Understood? But if you extra plot this graph, suppose then it will become parallel to the molar conductivity. That means limiting molar conductivity is not possible by drawing the graph. Is it fine? That is why we have to follow the Kohlrausch law of independent migration of ions. I hope you understood this thing. Okay. Now, see that the Kohlrausch law we have seen. Now we'll discuss the application of the Kohlrausch law. Basically, there are three applications of the Kohlrausch law. The first one is to calculate the alpha. Alpha is the degree of dissociation. Alpha is what? Degree of dissociation. Degree of dissociation means how much an electrolyte has dissociated. So the formula will be alpha is equal to molar conductivity divided by the limiting molar conductivity. This was given by the Kohlrausch law. This can be taken as equation number 1. So by using this formula, we can calculate the degree of dissociation. Now second one is to determine the Kc. Kc is the equilibrium constant. So if you calculate the equilibrium constant, last year you have seen in the equilibrium chapter. So if you take the CH3COH, it is dissociated to form the acetate ion H plus ion. So at time t, the concentration was taken as 1. Initially it was 0, 0, and at time t it was taken 1 minus alpha, and it will become alpha and alpha. Then finally we have to multiply all by concentration. Is it fine? Now, and Kc's value can be calculated by concentration CH3CO minus H plus upon CH3CO. That has been taught in the 11th standard so many times. Is it fine? So there is no need to describe it. So we have to substitute all these values. Instead of the CH3CO minus C alpha, the C alpha. Instead of the H plus C alpha, C alpha. Instead of this CH3COH, C into C minus alpha. Okay, the C to C is cancelled. Then what final formula is there? Kc is equal to C alpha square divided by 1 minus alpha. Is it clear? So this was the part. Now, after substituting the value of alpha, the Kc is equal to C into, if you substitute this value, cap m upon cap naught m, here this will become square divided by this one. After just rearrangement plus and minus, we get a final formula is equal to Kc is equal to C cap m square divided by cap naught m multiplied by cap m minus cap naught m. So this can be used for calculation of Kc. And third thing, we can calculate the solubility of the electrolyte. So this was an application of the Kohlrausch law. That's all for today. Okay, fine. We'll discuss the next topic in the next class.